Okay, so in this video, we'll consider an example of how we compute the probability that a normal random variable, in this case with a mean of 4 and a deviation of 3, lies between -1 and 11. And we'll see how we have to first standardize, and then how we can read off the probability with a table for the standard normal distribution. So the first step is we're asking, okay, we have x being a normal random variable with a mean of 4 and a deviation of 3. And we are asking for the probability that x is between -1 and 11. Well, the first step will be to standardize. We have to subtract the mean, divide by sigma to make the random variable become the standard normal random variable, therefore a normal random variable with a mean of 0 and a deviation of 1, because you'll see the only table that we have is for this special case of the normal random variable. So we first subtract the mean from every expression. So we'll have -1 minus 4 is at most x minus 4 is at most 11 minus 4. So we subtract from each term the mean, and then we divide everything by the standard deviation. So we divide by 3, divide by 3, divide by 3. So what do we have? The probability of -5/3, if you compute this, you will get -1.6 periodic, and you'll see the table that we have is only accurate to the second decimal place, so we always round up to the second decimal place. So here we'll round up to -1.67. Well, here we took the random variable x, we subtracted the mean, and divided by the standard deviation. So this is now z. It is now standard, and the second value, 11 minus 4, is 7 divided by 3, will give you, rounding up to the second decimal place, 2.33. So now, this probability is the same as this one, which is the same as this one, but now our random variable is z. So it is now the standard normal random variable. It has a mean of 0 and a deviation of 1. So we can draw a picture for this distribution. It will look something like this. You can use a little z, because now the variable is z. It is symmetric about 0. The deviation is 1, so it would look something like this. And we know that the probability that z lies between -1.67 and 2.33 will be the area under the distribution between these 2 points. So say -1.67 says here, and say 2.33 is here. So we know that geometrically, the probability that z lies between -1.67 and 2.33 is just the area under the standard normal distribution curve between the two values. The question is now, how do we compute this? Well, as you will see, we need the table for the standard normal distribution. So let's look at it for a second. There are two sides of the table. This is the first side, you see? It is only for the standard normal distribution, hence the normal distribution with a mean of 0 and a deviation of 1. And you see the table gives you the area below, underneath the curve, below a given value of z. So from -infinity all the way up to the z value. Now the first side of the table gives you the area below negative z values. The other side will give you the area below the distribution curve that are to the left of now positive z values. And now let's see how we can use this table to find the probability that we were looking for. Keeping in mind, all we have from the table is the entire area to the left of a given z value. But that's not exactly what we are looking for, right? We are looking for here the area between these two values. Well, let's redraw the picture and see if we can somehow find this in two steps. Suppose that we find the area below 2.33, the whole thing. Right? So this would be the probability that z is below 2.33. But now we're adding too much area, right? We're adding the entire area below the distribution curve for z to the left of 2.33. So what we get is all of this area, everything all the way down to negative infinity. Well, we have too much, right? We have to stop at negative 1.67. So the idea is, well, we've added too much area, so let's subtract the area that we do not want, and that is the area below negative 1.67. So if we remove this area from the whole thing, we'll be left with the area exactly between negative 1.67 and 2.33. And that is what we were after. Let's just remove the area where z is below negative 1.67. And there you have it. Now, each probability is the probability that z is to the left of a given z value. And now we can read both of these off from our distribution table. So let's look at the first value. Z is to the left of 2.33. This is a positive value, so we use the second side of our distribution table. Remove this. Okay, so for positive z values, where do we find the area in this table? You see, the row and the column will give you the z values, and the entries in the table are the probabilities. So we want the area to the left, if you remember, of 2.33. So we say, well, z is equal to, and we go down, 2.3, and we get the second decimal place with this. This would be 2.3, 2.31, 2.32, 2.33. So it will be in this column. So we go down this column where the second decimal place is 3. We go down, we go down, we go down. And we stop here. You see 2.3, 2.3, 2.31, 2.32, 2.33. So the area is 0.9901. Minus, let us now read this probability from the table, but because z is a negative value here, we will use the first side of our distribution table. So we're looking for negative 1.67. So negative 1.6 is here. This would be negative 1.60. This would be negative 1.61. Negative 1.62. We want the negative 1.67, so we are in this column. Moving down, negative 1.67. So the probability is this value here, which is 0.0475. And now we just subtract. With your calculator, do 0.9901 minus 0.0475, and you will arrive at 0.9426. And there you have it. The probability that the normal random variable with a mean of 4 and a deviation of 3 to lie between -1 and 11 is 0.9426. And this will always be it. No matter what your mean is and your deviation, all you have to do is standardize. Therefore, subtract the mean, divide by sigma, so you can then have the standard normal random variable. And then, once everything is standardized, always keep in mind that the table gives you the area to the left of a given z value, so you have to break them up, and then read both in the table, and then subtract, and there you have it. And it's worth mentioning a few other aspects of the normal distribution. And the one aspect that we've mentioned in the previous video was the symmetry of the distribution table. So if we consider a few examples of this, suppose that we looked at the following problem. We consider now the standard normal distribution. So we say, okay, it is symmetric about the mean, which is 0, right? Z is this. We will always use Z for the standard normal distribution. Hence, the normal random variable with a mean of 0 and a deviation of 1. What if, for example, I asked you to find the probability that Z is greater than, say, 2.1? So from the table, not the table, sorry, but the distribution curve, so I'm saying Z is bigger than or equal to 2.1. So geometrically, this would be the area under the distribution curve. To the right, Z is bigger than 2.1, so to the right of 2.1. So we are looking for this area. And you say, well, you can't find this directly from the distribution table because the table only gives you the area to the left of a particular Z value. Well, I'll show you two ways in which you can find this probability using, in one case, symmetry, in the other case, the fact that the area below the entire curve is exactly equal to 1. Let's first use symmetry. So our first solution, because the distribution curve is completely symmetric, about 0, if you reflect this part, about z equals 0, you'll get the second tail of the function, so this part right here, and 2.1 after you reflect will become negative 2.1. But because the distribution is symmetric, the area to the right of 2.1 is the same as the area to the left of negative 2.1. And now you have the probability of z lying to the left of a given z score, and this you can read from the normal distribution table. Because we have a negative z score, we will consider the first side. So we're looking for the area to the left of negative 2.1. So it's this side. Z is negative 2.1. Let's find the z value. Negative 2.1, right? And if you look up, negative 2.10, so it's negative 2.1 is this entry here, and the probability is 0.0179. So there you have it. This is simply 0.0179. That's one way of finding the area to the right of 2.1, being the area to the left of 2.1, and this we can read directly from our table. What if we wanted to find this using a different approach? This, I think, is the simplest method, but we can also use a different result. Let's reproduce the picture of the standard normal distribution. and we wanted the area to the right of 2.1. Right? This is what this is. So let's do P of Z is to the right of 2.1. So we only want the area of this part. Let's use the complement rule. Let's add everything. So the entire area below the distribution curve is 1. Now we've added everything. So we get the entire area. But we only wanted the area of this piece, the tail end. So we have to throw away the area to the left of 2.1 because we do not want this part. So we throw away the area where Z is to the left of 2.1. And now once again, this you can read from your table. It is the probability that Z lies to the left of a given Z score. Because the Z score is positive, we use the second side of our distribution table, and we're looking to the left of 2.1. So we find our Z score, right? This is the area to the left of a given Z score when Z is positive, and Z for us was 2.1. So this is Z is 2.1, and it was exactly 2.1, so the second decimal place is 0, so it's 2.1, and the probability you see is 0.9821. So this is equal to 0.9821, and if we subtract, so 1 minus 0.9821 gives us 0.0179, just as before. So you see we can find the probability of Z being to the right of 2.1, so the area of the right tail of 2.1, either using symmetry, about 0 of the distribution curve, which I think is the simplest method, but we can also use the complement rule. Find the entire area, which is 1, and then throw away the area to the left of 2.1, and you're left with the area of to the right of 2.1. Whichever method you prefer, knock yourself out. If we had a problem with an average or a sum of random variables, everything would be the same except we would have a different mean and a different deviation, and then we would still just standardize. Let's do one example with an average, and the sum works in the same way. Suppose we said that we have, let's go with 10 random variables, so x1, x2, x10. Suppose they are all normal random variables. And suppose they have a mean of, say, 19, and a deviation, say, of, let's go with 12. Suppose we now ask the following question. So you have these 10 random variables, and we ask, what is the probability so that the average value of these 10 random variables, so you add them up and divide by 10, is, say, at most, and we'll go with, say, 20. Then the question is, all we need is the distribution for x bar. If you remember, let's compute it here. Again, x bar is just the average, so we add these 10 random variables, and we divide by 10. And if you remember, this also follows a normal distribution. Now here, your mean is 19, and the deviation of each random variable x1 through x10 is 12. If you recall, the average will have the same mean, so it will still be 19, The deviation, though, of the average will be the deviation of the individual x's, so it will be 12, but now divided by the square root of the number of terms that you're averaging over. Here we're averaging over 10 values, so it'll be over the root of 10. And that is the distribution for x bar, the average of these 10 random variables. Well, now that we have the distribution for x bar, we want the probability of x bar being at most 20. All we have to do now is standardize. Well, to standardize, we subtract from both expressions the mean. So we'll have x bar minus 19 is at most 20 minus 19. And then we divide by the deviation. So we divide by 12 over root of 10. And we have now standardized. If you remember, if you have a normal random variable, if you subtract its mean and divide by its deviation, this is now standardized. So this is the standard normal random variable, therefore with a mean of 0 and a deviation of 1. Well, let's compute this now. This will be the probability that z is at most, well, 20 minus, and you can compute it here if you want, 20 minus 19, that's just 1. And if you divide by 12 over root of 10, if you divide by a fraction, that's the same as multiplying by the inverse. So you can multiply the numerator, which is 1, by the inverse of this fraction, which will be root of 10 over 12. And remember that the table is only accurate to the second decimal place, so you can round this off to its second decimal place. So root of 10 divided by 12 gives you approximately 0.26. And now we're good to go. We have the probability that z lies to the left of 0.26. We can read this directly from our table. Our z-score is positive, so we use the first side. We're looking for the area to the left of 0.26. Oh, sorry. We have a positive z-score, my bad. We have a positive z-score, so we use the second side of our distribution table. So z is 0.26, so 0.2, 0.2, 0.21, 0.22, 0.23, so we go up to 0.26, and the probability therefore is 0.6026. And so if you go back, we said, okay, we have 10 normal random variables, each with a mean of 19 and a deviation of 12, and we asked if we find the average of these 10 random variables, and we ask what is the probability that the average is at most 20, the answer after we simply standardize and then read off the probability from the distribution table, we get is roughly 60%, 0.6026. And that's it. So with these two videos, you should be able to attack every problem on the problem sheet for the normal distribution.